Welcome everybody. Welcome to our second lecture in the microcontroller course. And in this lecture we will cover, among others, or mostly, the sketch. So to do this we need to have a specific thing loaded. So open up your IDE and go to File, Sketchbook, BrightSparks, Bare Minimum. And that is the first sketch that we will be using. Alternatively, you could have gone to this button here, Open, BrightSparks, Bare Minimum. Right, let's see what we're looking at. A list of Arduino instructions is called a sketch. In computers, we refer to it as a program or as source code, but in the case of Arduinos, it's called a sketch. Now, everything that you see on the screen at the moment, everything in Bare Minimum, all of these characters must appear in all your sketches. And there's no exception. If one of these are not there, the sketch will not run. So remember that you have to have at least void space setup, brackets, brackets, curly brackets, close curly brackets, void, loop, brackets, brackets, curly brackets, close curly brackets. Those have to be there. So memorize them. Now, in our sketch, the separate lines are optional. We don't have to have separate lines. This could just as well have looked like this, and it would have run just as well. But I can assure you that when it looks like this, you're not going to understand it. So separate lines are optional, but they are appreciated by humans. And when we look at it like this, it looks much more understandable. Right. Now, also, for the sake of humanity, we can also indent in our sketch. So for instance, if I wanted to write something here and here and here, it's clear that that is inside the block that starts with void and ends at that point. And if we are working here and here and here, same thing, indented. Once more, it is optional, but you should do it. Now, as you noticed, this IDE, as we typed enter, it automatically went to an indented state. And if it recognizes some words, then it will automatically indent from that point. And you'll notice that it also automatically added this closing brackets because it recognized, it knew what I was going to do. Don't worry, you're not supposed to know all about that stuff, especially that garbage that I wrote there. That's what we're looking at the moment. Now, the number of spaces or lines between words are ignored. So, for instance, I could have done something like that, and maybe an extra bit of space in there, and so forth. Once more, this is not going to be very understandable, but it's legal. It will compile and write whatever we've written, which is absolutely nothing, to the microcontroller without any complaints. So the number of spaces and new lines are ignored. But we must at least have a space between two words. The poor computer that has to work out that that is two words, void and setup. Two words, it won't know it, and that will give an error. So we need at least one space between words, but any more than that are ignored. And also, around these non-word characters, like the bracket and the curly bracket, and maybe in a maths equation, the plus or the minus. Once more, you can have 0 or more than 0, in other words, one or more spaces between two non-word characters. So, for instance, I didn't have to have that space in there. I don't even have to have the new line in there. I do have to have the space between void and loop, but here I don't need any more than no spaces. But I might like it that I want to have an extra space there to make it stand out that that is my curly bracket, and maybe I would like to know that that is also by the end of my curly bracket. So we can put in, and if we have a maths equation, say for instance, A equals B plus 1, that's acceptable. But you might want to write which kind of looks a little bit more understandable, or even you might want to write A equals B plus 1, or A equals B plus 1 plus C plus 1. And you see why I've put in the space there. It helps us to realize that's in brackets and that's in brackets, and so forth. So the number of spaces are immaterial so long as it's not a space between two words, which has to be there. You'll also notice something interesting here. You notice my cursor's over here by that brace. You notice that brace up there is in a square bracket, a little rectangle. That tells me that that brace matches that one. If my cursor's by that bracket, it tells me that that bracket matches that one. And if my cursor's before that bracket, it tells me that one matches this one. So for instance, if I go 1, 2, 3, and another 1, 2, 3, you'll see because my cursor's there, it matches that bracket. Because it's there, it matches that bracket. Because it's there, it matches that bracket. Very handy function that this has that tells you when my cursor's on a bracket, it gives me the one that matches it, which helps a lot with finding errors, in other words, debugging. Right, so that's all about the spaces. Now, one more thing, and that is that if I want to write something down that the computer mustn't get confused about, I can do it by putting in a double slash. Everything after the double slash, the computer will ignore. Otherwise, it'll give me, if that double slash isn't there, it'll give me one horrible error because it doesn't know what that is. But once I put a double slash, everything after that in the line is ignored. So for instance, I can put a double slash and some stuff there. Everything from the double slash to the end is ignored. But if I want to put this bracket, I want to take it and write it up top here, then I have actually caused an error, because what have I said? Everything after the double slash is ignored. So even though we need to know that this little guy needs a mate, it doesn't help putting that in a comment because the computer has ignored that right from the start. So you can put comments anywhere, and you should put comments wherever you have something that you want to comment about, so that next time you read the program or the sketch, you'll remember what you did. Excellent. The only comment that is superfluous is no comment or whatever you like. You can never really put in too many comments, so long as they mean something. So that's basically what's happening in that sketch. Right, now let me give a couple more of explanations of what we see inside the sketch. Firstly, the words setup and loop in this context are functions. They are called functions because they are functional. They do something. And so both setup and loop, which we have learned have to be there, both of those functions have to be present in our sketch. Now, why there are two there is because whatever we have in setup, whatever we've put inside setup, and that's garbage, of course, but whatever we've put inside setup will be run when the microcontroller first switches on, always. So whatever's between those two brackets, those two braces, that will be run when the microcontroller first switches on. It will be run only once, and it will be run never again until you've switched off the microcontroller and switched it on again, at which stage it runs through the setup again and continues. However, the instructions inside of loop are run continually, forever. As long as that microcontroller has power attached to it, it will run whatever's in here and then run it again and run it again and run it again and run it again, continually, forever. So this is an interesting concept which is newish to people that are used to programs. You're used to the fact that the program starts and then the program finishes and then you switch off the computer and go to sleep. In this case, the program starts, or the sketch starts, runs setup, and then continues doing loop forever until it loses power. Now, another thing that we see in this, just take out this garbage, and obviously that is garbage. The other thing which we notice, or I must mention, is that here are two brackets, opening and closing bracket, there and there, and they are empty. There's nothing in there. That's the way they should be, and that means that we are not sending any information to this function. Sometimes we need to send information to a function. Say, for instance, I use the function print, and I send the information to it, print Cecil. Then I'm sending something to that function, which then functions. But in this case, we're telling it we're not sending anything to you. We just want you to do all the commands between that curly bracket and that curly bracket. And the same with loop. We're not sending you any information. We just want you to do from there to there, which of course now is empty, but very soon will be filled up. Right. Then, in a similar vein, but just the opposite, void, which is another word for empty. The earth was waste and void, emptiness. Void means setup is sending nothing back to whatever called it. So when we say void, we are saying don't send anything back. I'm not expecting anything back, and you don't have to send anything back. There's nothing going to come back when you're finished doing your work. And so those voids mean the functions don't return anything. Now these two curly braces, that one, and as you see they are marked as that one matching that one. That is called a block of code. So I can have something, and I have another curly brackets and something, and I have another curly brackets, something, and close my curly brackets. Then from here all the way to there is a block, and from there to there is another block inside of this block, and from there to there is a block inside of that block. And so each of these are a block of code, and we will refer to that by that name in future. A block of code is between two matching curly brackets. Now, we said earlier that we don't really need to have a space or a new line between our different instructions. So for instance, I could write an instruction A equals B plus 1, and then another instruction C equals D plus 10, for instance, just for example. Now, here are two instructions, okay, called expressions. That's the expression which is being written into A, but don't worry about that at the moment. Here we have two instructions. And theoretically, I told you that you could take out these spaces. Okay, so I've led you up the garden path to a certain extent. Not really, but yes, we can take out those extra spaces. But we have actually caused the compiler a little bit of a headache, because between the 1 and the C, it doesn't know that that stops there and the new one starts here. It doesn't know that those are two instructions, that instruction and that instruction. two different instructions. There's nothing here in between to tell him that. So, as a result of the fact that we can add and take out as many spaces as we like, we are now forced to do something after every single instruction. We need to end it with a semicolon. So, A equals B plus 1, semicolon, end of instruction. We don't have to have a new line. C equals D plus 10, end of instruction. End of the block. So just by putting in those two semicolons, we have told the compiler, who wants to convert this into something to send to the Uno or the Nano or the whatever Arduino, it knows that those are two separate instructions. And for the sake of humans, yes, we'll write it like that. But even so, after every line where an instruction ends, there must be a semicolon. This is must, and if it's not there, it's going to give you funny errors. Right, the time has now come for you actually to grab a piece of hardware and start working with a microcontroller. So we are now going to connect up your Nano. So the first thing you want to do now is to look for your Nano. This is our Nano, and according to the instructions that I gave to prepare for this lecture, you will have soldered in that group of legs and soldered in that group of legs and soldered in these legs. These aren't soldered in, but that's what you should have done. So there our Nano has its connection points soldered in and ready to be used as we go along. Right, now we take our USB-C connector. And on this side of the connector is our normal USB plug that plugs into your computer. Of course, if you have a computer that doesn't use this type of plug, then you need the type of plug that your computer uses. But for the most part, computers use this plug as their USB talking to the outside world. However, the very new computers use USB-C to talk via the USB. So whatever your computer does, you need that on the one side of the wire. Then you need this on the other side of the wire, a USB-C plug. And that is now going to be plugged into your Nano. The way to recognize the USB-C, and I'll try and get it a bit into focus, is that the end is completely rounded. If there are any square corners to the connector, it's not USB-C. So here we have our USB-C, and we are going to connect it to our Nano. And that's the big advantage of USB-C, and that is that it will connect either way up. I'm sure you have often tried to put in your USB connector the wrong way around. In USB-C, there is no wrong way around. Fine, so now I'm going to plug that into my computer. And as I do so, a light comes on. And you see next to it, power. So that tells us that the computer is powering the Nano. It's not talking to it yet, but it is powering the Nano. And then you see another little one that has an L next to it. It happens to be flashing, but that's as a result of the program that is, or the sketch that is currently loaded into the Arduino Nano. So the big thing is that power light must switch on to tell us that our Nano is running. Fine. Now let's talk to it. First, we must set up the board. Set up our IDE to tell the computer what type of board we have. So we go here to File and click on File. And down comes the drop-down menu of all the things that we can do for File. And of course there's one for Edit and Sketch and Tools and Help as well. But at the moment we're going to look at the File one. Go down to the one, sorry, my apologies, we're not going to look at File, we're going to look at Tools. Go down the Tools list and you'll see the various things, the various tools that are available for our IDE to work with. And one of them is this one that says Board. And as you hover over it, you'll see this comes up, Boards Manager and so forth. Now, probably when you hovered over it, a whole list came up, right? The fact that there's not a big list is that I've also loaded another type of board onto this IDE, and so it says those are all the Arduino boards and those are all the ESP8266 boards. So whether you have Arduino AVR boards there or the whole list immediately, you need to go up and down and look for Arduino Nano. And you click on that, and that will then change your IDE to be set up for an Arduino Nano. Then we go back to Tools again, click on it, go down, there's our Arduino Nano that we just set. Now, what processor? It'll say, okay, either the 80MB128 or the 328, and then the 80MB328 with the old bootloader and the 80MB168. The answer is the Nano that we have is the 80MB328 with the old bootloader. Old doesn't mean antiquated, it's just there are two available and the guy they called the one old. So we click on that, and when we go back to Tools, click on Tools, we'll see there processor 80MB328 old bootloader. Right, now we have to decide which port this is connected to. And when we hover over that, we'll get next to this a list of the available ports that are available on our computer, that the computer thinks you might be connected to. And this, if you have a Linux computer, will have these dev TTY stuff in there. And if you have a Windows computer, you'll have COM3, COM4, COM16, whatever it is, will be in that list. And I can't tell you which one your computer connected to, and so it's going to be a matter of trial and error. So when we do this and actually run something, we'll see if we have got it wrong. So on purpose, I'm going to click that one, which I happen to know is wrong. So I'm just going to take this out because that's not necessary. And now that we've set up the board, right, now that we have set up the board, we can now load our first actual program that actually sketch that actually does something. And so we're going to go to, for experiment 2, we're going to go to Files, File, Sketchbook, BrightSparks, Blink. Okay, so we're going to go there, or alternatively we can go to the Open button up there, shortcut button, press that, go to BrightSparks, Blink. Okay, and that means we have loaded up this sketch, and we're now going to try and run it and so forth. So we go and first we try and run it, and then I'll explain what's going on. Okay, so we're going to try. Remember, I set the wrong USB port, so it's not going to work, but let's see what is working. Firstly, it's handy to have a whole lot of debugging information available, especially here at the beginning. So I'm going to go to File, Preferences, and here I'm going to click on Compilation and Upload. Right? So if those are not filled in with the blue dot, then click on them so that they are filled in with the blue dot. That will give us a lot more information as to what's going on, most of which we won't understand, but at least one has an idea what's happening, and that will help us in our compilation. So we've set that, and we go OK. Right, now we go, and remember this button was try out the sketch and see what it looks like. So that's what we're going to do. We click that, and you immediately down at the bottom see a whole lot of white lines going by. And yes, you're not going to need to understand all of them, but the important thing is right down here at the bottom, it says sketch uses so many bytes, global variables use so many bytes. Okay, that's the sign that all's going well. If, for instance, I get rid of this closing brace, curly brackets, we know that that's wrong, but just let's try it. Now if we try out the program, you'll see exit status 1, function definition is not allowed here, and so we know that we've got something wrong, and later on we'll kind of learn how to understand what these messages mean. But for now I'm just going to put the bracket back in again, try it out again, and all is well. Sketch users, global variables used, fine. Okay, now we're going to upload it to our Nano. So we go over here and click on the Upload button. Okay, and we look, and nothing seems to be happening. I can make this a bit bigger. Now it says something's happened, but now it says programmer is not responding, programmer is not responding, and so forth. And that is a typical mistake which you'll see when you have not got your USB port correct. So while it's busy, it tries it 10 times, and I'm not going to stop it for now, just so that it's because that can make life more complicated. So we'll let it finish with its 10, but we'll go back to Tools, Port, and I can try that one, but let's do that one first. Sorry, somehow it didn't want to listen to me. Click on that one. Okay, so now if I look at Tools, I'll see my new one, and you'll see that the blue dot is now down at the bottom. And if you struggle, just plain and simple, try for each one of these that are there. And if nothing's there, it means that you don't have the drivers. But I tried to have them all available for you when I installed this, so they should be there, and you should be able to just see the COM ports or the TTY ports that are available and choose the correct one. Okay, it's a long story, but it is frustrating if it doesn't work. So we're going to try again. Try uploading. And the minute we see these hash lines, writing, reading, everything's fine, and it's verifying, and it's checked that those bytes are correct, have written correctly, and it says AVR do done, thank you. Usually, of course, you just see the bottom line. And when you see that, you know all's gone well. Okay, all is calm on the Western Front. Right, now let's have a look at the program that we did write. Actually, that I wrote and you are looking at. And these programs, I've got them from, some of them are just adaptations of the examples that Arduino has published. Some of them I wrote on my own volition, etc., etc. So this is the first one for this course, 02 blink, and as you guessed, it causes something to blink. Excuse me. So we have here some new concepts. Firstly, the concept of a constant. What's a constant? Well, a constant is a constant. You know, red is red because red is red. And a constant is constant because a constant is constant. And built in to the Arduino compiler are some constants that they have defined for us, and we don't have to worry about them. They're already defined. And typically a constant is written all capital letters. Okay? So if it's a constant, it's not necessary. Constant could be written in any letters, but the name of a constant is typically given in all capitals. And here we have 4 constants that we see here in our program. We have LED built-in, output, high, and low. And so those constants, as I say, are built into the actual compiler. LED built-in. When we were looking at our Nano, we saw that little LED that was given a little flash with an L next to it. That's called the built-in LED. And that's connected to some other number, data number on the Nano. But the Arduino has saved us the trouble of finding out which one it's connected to, and it has just got here the value that will get the LED, the built-in LED, for you to access it. Then here's another one, and it says output. Well, exactly that. When we use that, we define whatever we're talking about as being an output. And then we have high, which refers to the voltage that happens to be on those various pins. And high means round about 5 volts for these microcontrollers. Others work on 3.3, but because the different ones work at different voltages, we say high is the highest voltage that it knows about, and low is the lowest voltage that it knows about, kind of 0 volts, close to 0 volts, or connected to ground is another way of looking at it. So here we have those 4 constants that we actually are using in this sketch. Along with these 4 constants, we have 3 functions. Now, we've already seen the function called setup, and we've seen the function called loop, and now we see 3 more functions that we can use. And they are once more defined by the Arduino compiler. The first function, pin mode, means that we can set the mode of the pin. In other words, you might have guessed whether it's output or input. Digital write function means that we write a value or tell that pin what it must be, either high or low. And then delay is exactly that. It delays for a length of time before it does the next function. So let's see how these that we've looked at here actually are used inside of our sketch. Right, so as you remember, setup is run once. So we're going to put in there everything that we need to set up our microcontroller. And in this case, we just want to say that whatever pin that LED built-in pin is, it's got a number, but at the moment I'm not worried. Whatever that pin is, I want it to be an output pin because I want to flash the LED. So I want to tell it to do something rather than ask it what's happening. So I define pin mode. I set the mode of this pin, LED built-in pin, to output. That's all I need to set up my system. Then I run the loop. And remember, the loop is going to go over and over and over again. So I run the loop, and the first thing I do is digital write. In other words, I write a value or I output a value to a pin. And what I'm telling it here is take this LED built-in pin and make it high. In other words, round about 5 volts. And if we had an oscilloscope or a voltmeter connected to this pin, we would see that it's round about 5 volts. And then I said delay for 50 milliseconds. Okay, so now what is a millisecond? Well, a millimeter is 1,000th of a meter, so a millisecond is 1,000th of a second. And so this says 50 thousandths of a second. Do nothing. Wait. Hang around. Then, what do I do next? Digital write, same function, same pin, but this time I want to switch it low. In other words, about 0 volts. So the light is not going to light up. And after I've done that, I delay for 1,000 milliseconds. In other words, 1 second. Now that I've finished doing that, my program is not finished. It just goes back to the start of the loop and does it again, and does it again, and does it again. And so we expect to see a little bright flash for 50 milliseconds, and then an off for a whole second, and then start the flash, wait 50 milliseconds, switch off the flash, wait another second, over and over again. So let's turn to the camera, and that's exactly what we are seeing there. Little flash, 50 milliseconds, and off for 1 second. Okay, so let's just make sure that I'm not fooling you and telling you that it's working and it isn't. So what we're going to do is, I'm now going to make this on flash much longer. Let's make it 5 seconds. Okay? And then the off is going to be 1 second. Right? The minute I've changed that, I just go back to upload, and we see hashes and what have you, AVR dude, done. So now we look at that light, it's on for a long time. 1 second, 1, 2, 3, 4, 5. Off. 1, 2, 3, 4, 5. 1, etc. Okay? Or we can make it flash very fast. 50 milliseconds on the one and 50 milliseconds on the other. So it's now going to be on and off every 50 milliseconds. Up to the upload button, and I'm going, sorry, just switch off my camera. Okay, sorry, I was doing this behind your back. We've changed that to 50 and 50, and we are going to upload it. Sorry, wrong button. And hopefully I'll be able to see it. Sorry, there we are. My camera's battery has just died, but it's got the last little bit of battery to show you what's going on. And I'll switch it off again, and we'll go back and change this once more, and let's say a very short flash, and then a half a second delay. Okay, push on the button, upload, and I'm going to open this up so you see a little bit more what's going by. Upload, and it's done. And if I now switch on the camera again, there we are. So it just gives you little short flashes and half a second in between. So you have completed your first sketch with a little bit of help from my side, but now you can go and, just using what we've learned, you can just try and do various possibilities and upload them to your Nano and see what they like. And once that's done, we'll see you next week.